Okay, so far we have an example of a self-enforcing rule, that whole beach driftwood example that we kick things off with. This rule, the first on the beach can establish the property right, is an example of a convention followed by those people in the area. From this example, the author stated that, quote, he was trying to explain how rules or conventions regulating human action can evolve without conscious human design, and also how they can maintain themselves. So that's the goal, is to see how do these conventions evolve, how do they come about, and how do they maintain themselves? How do they stick around? Understanding these conventions can help us explore what we view as rational. As Hayek argues, conventions are the unplanned consequences of a process of evolution, and yet they create the order of our world. We will see, as Sugden argues, that the order in human affairs can arise spontaneously in the form of conventions. These rules are not the result of any process of collective choice, nor do they result from any kind of abstract rational analysis in which individuals are modeled as having unlimited powers of deductive reasoning, but no imagination and no common human experience. In this sense, at least, conventions are not the product of our reason. So Sugden is arguing that these rules that we're following come from this evolutionary process, from spontaneous order. And Hayek is arguing that these conventions, these rules that we follow, can be what helps create the order that our world has. And so what we're going to do is we're going to really focus on this idea of conventions and how do they come about and how can they stay in place and how do they create order. And so in the next section here, the next section of the paper is called Conventions. We're going to start to use game theory to model conventions in order to help us consider their becoming and their sustainability. All right, so here is where you are going to start using game theory to understand and to represent the arguments of this paper. When the next slide comes up, go ahead and pause the video again. But when you're reading, draw up a payoff matrix like the one that is shown, but utilize the payoffs that are described in the paper to fill all of the numbers into that payoff matrix, right? So on the next slide, you're going to see a payoff matrix, but there's going to be no payoffs listed. Go ahead and get the payoffs from the paper and put those into that payoff matrix so that you can continue moving forward. So the paper states that you have a Nash equilibrium as long as, quote, the strategy selected is the best reply to the opponent's strategy. This is basically the same thing, or another way of putting how we define Nash equilibria in intermediate micro, where we say that you have a Nash equilibria so long as no one can do better off holding the other player's actions constant. In this game, there's 3 Nash equilibria to consider. First, there's 2 pure strategy Nash equilibria defined. So before moving on, make sure you identify the 2 pure strategy Nash equilibria in this game. Sugden is going to argue that these are the stable equilibria in this example. So let's go briefly back to his paper. All right, so what you want to do now is prove to yourself that in this game, that both players, player 1 and player 2, has a mixed strategy Nash equilibria of playing Hawk with a probability of 0.33, or 1/3 chance of playing Hawk. So when the next slide comes up, pause the video and work through the math to show that player 1's mixed strategy Nash equilibria is such that the probability of playing Hawk, the probability of Hawk is 1/3, and the probability of playing Dove is then 1 minus P, or 2/3. You should note that in order to find player 1's mixed strategy Nash equilibria, you need to make player 2 indifferent between her 2 options. And you should also note that once you solve for player 1, since the game has the payoffs the same for both players, you've basically already solved for player 2. So you really only have to do this for one player. All right, so to calculate the mixed strategy Nash equilibria, what you should have done is started off by recognizing that player 1 is going to play Hawk with this probability of P, and that means that they're going to play Dove with this probability of 1 minus P. Once you start off with that and you identify what the probability of these different payoffs player 1 is going to play in this theoretical sense, we can start to calculate the mixed strategy Nash equilibria. So for player 1, the mixed strategy Nash equilibria is such that the payoffs for player 2 between playing Hawk and between playing Dove should be equal. Right? And so we need to make it so that player 2 is indifferent between those two options, between playing Hawk and playing Dove. Right? And so what we could do is we could say, okay, well, player 2, we want to think about how much of a payoff do they get from playing Hawk, right? And so what are they going to get? Well, they're going to get -1. But how often are they going to get -1? Only with a probability of P, because that means that player 1 has played in this row right up here, right? So we've played in this row, then that means, okay, we're going to get this payoff of -1. So we're going to get this payoff of -1. How much? How often? P times. But then we have to figure out the entire payoff for Hawk. And there's another option where player 2 gets a payoff of 1. And how often do they get that? They get that this 1 minus P. So we're in this row here, right? So we're going to get this payoff of 1 minus P times. So we can do plus 1 times 1 minus P. And what we have to do is we have to make that equal to player 2's payoff from playing Dove, right? And so we want to see, all right, what is player 2's payoffs from playing Dove? We need to make it equal to that. So we have this equal to the payoff from playing Dove. Well, they get 0 times P. So we have this, 0P we could put in there, plus the other alternative, if player 2 plays Dove, is that player 2 ends up with 0.5. Well, how often do they get 0.5? They get it 1 minus P amount of the time. So we can have this 0.5 payoff times 1 minus P. So that's the basic setup that you have. And then from there, you can go ahead and just reduce everything down and solve for P. What you're going to end up with is something that looks like, if you reduce this down, and then finally you can solve, and P is equal to 1/3. So we have proven that you have P equal to 1/3, or that you play Hawk 1/3 of the time for your mixed strategy Nash equilibria. Now the same thing could be said for player 2, since the payoffs are symmetric here, that player 2's mixed strategy Nash equilibria is also to play Hawk 1/3 of the time. So what I want you to do here is analyze the self-sustaining convention statement that was just given by considering our setup, right? So in this game, you can see that you and I are playing this game, and I receive the A signal. I'm player 1, right? And I receive an A signal. So the focal move for me in this situation, player 1, is to play Hawk, and for you to play Dove. Right? So that's what signal A is representing here, is for me to play Hawk and you to play Dove. Do you have any individual incentive to cheat this arrangement and deviate from this focal strategy? Right? So we should be playing in this quadrant, this cell right here. Do you have any individual incentive to move away from this setup? So if you're looking at this just purely as player 2, we can see that your payoff is 0, right? And in this setup, you know that I am playing Hawk, right? So the question then becomes, do you have any incentive to change your behavior from Dove over to Hawk, right? Well, if you did, you would pick up a payoff of -1. -1 is less than 0, so you do not have any individual incentive to cheat this setup. If you did play Hawk instead and I stick to the focal point of playing hawk, your payoff is now -1, and so you have no individual incentive to move. We could also look at this and say, do I have any individual incentive to change? Right? So in this situation, we say, okay, we're in this same cell. The focal point should be that I play hawk and you play dove. If you were just given this game and we had this big blue rectangle around this payoff here of hawk dove, where player 1 gets 1 and player 2 gets 0, we could imagine that this signal has been received by both players, and this is our focal point that we are going to play. Does player 1 have any individual incentive to deviate from this situation? Well, we can imagine the focal point holding, and player 2 receives this signal, and we could imagine player 2 sticks to playing dove. Player 1 is only concerned with their own payoffs. Payoffs from playing hawk would be a payoff of 1. Does player 1 have any incentive to move from playing hawk down to playing dove? Well, if player 1 does deviate on his own, the payoff would only be 0.5, so there is no incentive to deviate from this as an individual in this situation either, right? And so we have no individual incentive to deviate from this situation. We should expect to see, if this signal is received, that this is the focal point. We should expect to see this be played.
Remember that our hawk-dove game has 3 Nash equilibria. Schelling showed that games like hawk-dove cannot be solved in this way where we know the outcome for sure. Best case scenario is perhaps that we could claim that both people will play the mixed strategy Nash equilibria, and then we probabilistically know where they end up. So go ahead and pause the video and calculate the expected payoff from each player playing the mixed strategy Nash equilibria. So if both players are playing the mixed strategy Nash equilibria, what are the payoffs that we expect player 1 and player 2 to end up with? We will then use this with the arguments of the paper in order to contrast the mixed strategy Nash equilibria play with other alternatives, such as utilizing conventions or focal points and things like that.
All right, so here let's calculate the payoffs that we would expect to see if both players played the mixed strategy Nash equilibria. So we already know that each player will play hawk with a probability of 1/3 according to our mixed strategy Nash equilibria calculation. So both of them are going to play with a probability of 1/3, which means that they're going to play dove with a probability of 2/3 here. Right? And so what we need to do our mixed strategy Nash equilibria calculations is go forth and say, what is the probability that we're in each of the cells? So what's the probability that we end up at hawk hawk, at dove dove, at hawk dove, right? At all the different cells, we need to calculate what's the probability that we're actually here, right? And so what we can see from this basic setup is that we can say, okay, well, player 1 will play hawk at 1/3 here. They will play 1/3 here. They will play 2/3. They will play at this dove amount. So we can say 2/3, 2/3, right? And then we can look at player 2. We can say, okay, player 2, you're going to play hawk 1/3 and 1/3. And we can note that you're going to play dove, right? 2/3 and 2/3. So from this, what we can do is we can just multiply these fractions by each other to figure out what is the probability that we're actually in this cell. So we can take both of these fractions here in the hawk-hawk cell, right, to figure out, multiply them by each other to figure out what's the probability that we are here in total. So if we have 1/3 and 1/3, we can simply reduce this and say, all right, now we know there's a 1 in 9 chance that we're at this cell, right? We can take for the hawk-dove outcome here, we can say, all right, 1/3 times 2/3. Say, all right, 2 in 9 chance that we are here. Same math holds down here. 2 in 9 chance. And then 2/3 times 2/3 for our last cell here. And we can have that be our 4/9, right? So you can see we have an overall probability of 1 here. So hopefully our math checks out. And now what we have to do, though, is we have to take these probabilities that were in these cells and multiply them by each player's corresponding payoff. And so we'll just do this for player 1 because it's a symmetric game. We know that if we understand what's happening for player 1, we can quite easily figure out what's happening for player 2. And so all we have to do is we have to say, okay, well, here's our probability, right? We know this is the probability that we're in this cell. And then we have to say, okay, but what's player 1's payoff if we're in that cell? And here's where we can look at the game that we have, the setup of the game that we have. Say, okay, if player 1, if we're in that cell, we get a payoff of -1. And so all we're going to do to find player 1's payoff here, their final payoff for this cell, is going to be to simply state, all right, 1/9 times this -1, and that's player 1's payoff. So we end up with player 1's payoff being -1/9. Right, and so we can do the same thing here. We can look at this cell. Player 1's payoff is 1. Multiply that by 2/9. And what we end up with is 2/9. So player 1's payoff there would be 2/9. Here, really easy one. The payoff is 0 if we end up in this cell for player 1. And so what we're going to do is just have a payoff of 0. And then player 1, what would they expect to get in this cell? 0.5. 0.5 times 4/9. And we can say, all right, we're going to have 4/18. So this would be our expected payoff from these various cells, given the probabilities that were in these cells. And then what we have to do is we have to add all of these together. When we add together -1/9, 2/9, and 4/18 plus 0, what we end up with is 6/18, or 1/3. So our overall expected payoff from this game is 1/3. When player 1 plays their mixed strategy, if they played it a whole bunch of times, right, on average, the payoff would be 1/3 if playing against another player playing that same mixed strategy, right? And so that would be the basic mixed strategy Nash equilibria expected payoff. That's what we would expect to see as an outcome of this game with people utilizing the mixed strategies.
All right, so now that we have the mixed strategy Nash equilibria expected payoffs calculated, let's hop back into the paper. We just covered Schelling's emphasis that the standard economic approach to rationality does not generate an answer, and yet average people come up with not just an answer, but often a good one in the real world all the time. Or as it was stated in the paper, the ideally rational but completely inexperienced players of classical game theory. This is the hyper-rational neoclassical economic agent. Right? These people would, quote, find they had insufficient data to determine what they should do. Whereas in contrast, ordinary people with limited rationality, but some degree of experience and imagination, might have no difficulty in coordinating their behavior.